Welcome back to UBC CS 532W, Graduate Probabilistic Programming, and today is Lecture 9, where we're going to talk about a non-standard interpretation of a first-order probabilistic programming language. In other words, we're going to talk about how to do graphical model compilation. And for those of you who are working on the homework, you will have almost certainly run Daphne by this point. How many of you have run Daphne? Okay, almost everyone, except for Jason, apparently. So what we're going to talk about today are things that are implemented for you. Okay, so in some sense, you could actually, tune out, not pay attention, not care, whatever. So I'll give you that out if you want to, because it's been implemented for you. However, there's at least one of you I know for sure who should pay attention to this, Ryan, because eventually he will want to do something like this or understand how to do it himself for his own research, because I know what he's working on. And as well, you may, if you're interested, you may. Well, I should say, last year writing the compiler was one of the homeworks. It's still available as a homework, and you can do that if you want to, just to impress me. It's one of the extra homeworks. It's a little bit orthogonal to the inference message of the course, but if you haven't seen the kinds of things we're going to talk about today, it's good for you to be able to read the kind of notation we're going to look at today and to think in the way that we're going to talk about today, because, well, it will help you reason about how to write your evaluators, because your evaluators are basically implementing these rules, but just under a different semantics. Okay, so up to now, we've got graphical model correspondence. We've pointed out that some important properties of joint distributions could be programmatically derived from graphical models. In particular, figuring out the Markov blanket for each variable automatically. That's a very useful thing for your Metropolis within Gibbs inference engine that you will implement in homework 3. We pointed out that the link functions are usually left out from graphical models and they're put in the mathematical notation. However, in our case, we'll definitely put them in, and in particular, a lot of the focus of what we do is about writing down those link functions in a more explicit way, such that we can compute automatically in the way we'll talk about for homework 3. We know that you can denote, graphical models or finite variable cardinality probabilistic models using programming languages that are suitably restricted. Unfortunately, you have to put some funny limitations on the languages in order to make sure that correspondence actually happens. But it's not the worst thing in the world, because you can make the teeny tiny little FOPPL a more tolerable language in which to write by introducing sugar that aids readability and ease of programming. So today we're going to continue to focus on these static computation graph models, and we're going to talk about compiling to a graphical model representation. And what I'd like you to get out of this is an expanded notion in your mind of what compilation means, which again is to translate an expression in one language into an expression or data structure in another language in which the meaning is agreed. So today what we're going to talk about, and I hope for a pretty high degree of interactivity, because some of this is pretty confusing the first time you see it, and it's frankly a little easier to read with some guidance. We're going to talk about going from a FOPPL program like this, or any program, right? We've talked about desugaring, or at least we've talked about the presence of sugar, and you can sort of understand how to do desugaring in terms of just string rewrites. Right? Today, we're going to talk about what I'll refer to as translation rules, which, when systematically followed transform programs in the FOPPL language, in the desugared FOPPL language, into a graphical model data structure with link functions that are expressions in the pure deterministic language that we talked about. In other words, no sampler observe expressions. And this graph is going to be a data structure or expression that we all agree on the meaning of. I see a question being typed right now, or some sort of text messaging going on, where there will be vertices. These will be random variables. There'll be adjacencies. These will be edges in a graph. And there will be link function expressions where the value of these expressions we will agree is provided by some implementation or semantics of the underlying pure deterministic language. In particular, these expressions, as I told you, will be expressions that evaluate the density of the random variable given its parents. Okay? There will be a collection of value assignments to the random variables whose values are observed, and there will be an expression which computes the return expression given random variable values in the graphical model or program. Okay? So there's a funny thing that's going to happen here. So, we talked a little bit about quote unquote running such a program, right? Now we're going to talk about a non-standard evaluation of such a program, running it in a different way. And running it in a different way means consuming this program and making this output, not returning Z, but actually returning this entire GE pair where G is structured again as a set of vertices, a set of adjacencies, a map that allows you to compute the probability density or probability mass function for the random variables, and a set of bindings for the random variable values. Okay, so the point is that we're going to go from here to a graphical representation, literally of a graphical model, in which, again, there are vertices for every random variable. There are edges between all the random variables. There is a set of expressions that allow you to compute the density or mass of a random variable given its parents. A binding of observed random variables to their values, and a return expression which consumes values, which has potentially vertices of the graphical model in its expression. Okay. Any question about this?
I have a question.
Great. Awesome. Starting off early.
So, very surprising, I know. So on the left-hand side where it's rho phi E down arrow GE, does that just mean rho phi E are like parameters that feed into defining G and big E?
No, we're going to go through this in horrible, hideous detail, and you're going to thank goodness by the end of the lecture that you're not a programming languages person yet, or you're going to either think, oh my goodness, this is notation that actually makes sense for the first time in the entire course.
Okay.
So, perfect. So let's start. Okay. So this is there's a bunch of different forms for the PL people. For instance, maybe Mia can I think Mia, I keep holding you out as the PL person, but I'm guessing Adam has some PL background. Maybe there's no PL people in this course, which will be really highly entertaining. But there's a bunch of different forms for writing down semantics of programs, which again, a semantics for a programming language. Maybe James can weigh in here. Is again assigning meaning to expressions, right? And in order to assign meaning to expressions, effectively, you have to write a recursive procedure in order to reduce those expressions into values in some other language or system Okay, so this basically translates to or corresponds to or means. It is the assign meaning to expression symbol, right? So when we talk about compilation to a graphical model, we're going to have a bunch of translation rules, and these are rules of inference, or they're referred to, or in our case, these will be big step operational semantics. And there's really, again, there's a bunch of notations for this, and the meanings that are given or semantics that are given to a particular language are described by mathematical syntax that looks like this. What's on the left and what's on the right changes, but this translation, as in like, I'm going to assign meaning to this stuff over here, and the meaning is the stuff on the right. That's what it means, assign meaning, okay? So in our particular context, this row is going to be a mapping from procedure names to their definitions, okay? So that's basically a lookup of the defins that your program has, okay? If you remember the syntax, there's defins, bunch of defins. This is going to be just a map of those. Phi is something whose meaning will only become apparent after we go through this, is going to be a logical predicate for the control flow context. Control flow means if you were to run the program the way we've talked about, it means which of the predicate, which of the consequent alternate branches you've gone down at every conditional branching opportunity or statement in the program. Okay? This will become clear or clearer. And E, this is an expression we intend to compile. So ultimately, this would be at the very beginning of the compilation procedure, the entire body of the program, right? Modulo or minus the defins at the top. Okay? This expression is translated to a Bayesian network or graphical model G and an expression E in the deterministic sublanguage, which we talked about in the last lecture. That's the end, right? The expression E describes the return value of the original expression, or program E, in terms of random variables in G. Vertices in G represent random variables, and arcs dependencies between them. For each random variable in G, we will define a probability density or mass in the graph. That will become apparent in just a second. For observed random variables, we additionally define the observed random variable as well as the logical predicate that determines whether or not the observed expression is on the control flow path conditioned on the values of the latent variables. Okay. Sorry to put all that text on a slide like that, but there's literally no way I would be able to remember it and accurately, reproduce it without.
I have a quick question about
Awesome.
that. So the way that you described it verbally, or on the pictorially on the previous slide, it looks like G and E, you define that, and then that gives meaning to rho, phi, and E. But on the next slide, the way that it's written out in words, it looks like rho, phi, and E are known, and then that is then translated to return G and E. Big E.
It's translated to return G and E, no question about that. And it's the same here. This is the program. This is E. This is little e over here.
Mm-hmm.
Okay, and I haven't told you what So row here is empty. Sorry, row is empty. There's no defin here, right? E is this entire program.
Okay.
And I haven't told you what phi is. But I believe, this is just me remembering and guessing, phi would be true.
Okay, and so then that is translated to return this big G, big E.
So the meaning of a FOPPL program is going to be a value in the space described by the set of graphs, or Gs, which have vertices, edges, link functions, and value bindings, plus an expression. Okay, and the semantics that we're establishing only go so far as to establish the semantics of the graphical model. The semantics of the expressions require a further semantics for those expressions, but the semantics of those expressions we expect to be not in question, because it's basically function application and primitive values, and that's it, right? So it's like plus, minus, times, whatever, right? I don't even believe. Yeah. Ryan, you're
Sorry, you said something is in the space of something, and can you repeat that? I missed it.
Sorry, I'm saying that the meaning of this program will become a value in the space. If G lives, in big G, where big G is the set of all possible vertices, the set of all possible edges between vertices, right? It's a very, very richly structured high-dimensional space in which G can live, but there's nothing mysterious about that space. There are vertices, there are edges. We all agree what the meaning of vertices and edges are, right? There are link functions. There's nothing untoward or unusual about a link function, right? It's just a deterministic expression that links values to other values, right? Or density functions in our case. There's nothing untoward about variable bindings, or like basically assigning values to variables. And there certainly is nothing untoward about an expression in a deterministic language, right? So the space is G cross whatever big E here, right? Where G is itself richly structured, but everything in that space is nice, and we can sort of agree that we know what it means. Okay.
Can I ask a question?
Yeah, please.
Is there, so if like at the end of the day, all these link functions under P, they're also just expressions, right?
That's 100% right.
So is there some principal difference between the expression on the left that evaluates to a graph and the expression on the right that evaluates to the link function? Like, can you tell those apart? Like, is there something different about them, or are they fundamentally the same?
Well, so the point is that these expressions, these link functions, have no random variables. There's no sample or observe statement in them. Right?
Yeah.
So what we've done is we've taken a language in which there are these random elements, and we're going to effectively compile it into a representation where the random elements are separated out completely, so we can deal with them in our general purpose inference algorithms, because we know what to do with those in those cases. And everything else is deterministic computation, which we assume is done in a totally standard way, right?
Gotcha. Yeah.
So we have to define P burn and P norm, or
yeah. So P burn would be the probability of the value Z under a Bernoulli distribution with parameter 0.5.
At this point, that's like a primitive?
That's a primitive, yeah.
Okay.
Oh, yay. We're talking each other's language. This is great. Okay, this is good. Yeah, so, for those of you and us who are sticklers for notation, and we've been kind of fast and loose up to this point, we're about to get really serious about notation, right? So this is not terribly ambiguous because we've laid out the expressions here for the link functions, right? But these two, basically, this is just a graphical representation of what we're actually compiling to. So we're taking this expression, which is hard to deal with, right? Hard to reason about, and we're going to make it really, really concrete, what it means. Okay. Cool. But before we go into the translation rules, which I promise you are tons and tons of fun, we do have to think about a couple of things first. Okay, and they indicate some choices that are non-trivial about the design of languages and their semantics. Okay, so I would ask you to all read and tell me whether or not these two programs are equivalent in the sense of meaning the same or not the same posterior distribution over their return value Z. How many are on the side of yes? How many of you are on the side of no? Okay, so let's just go through it really quickly, right? So this is a Bernoulli random variable. You're gonna have a mixture model, and it's gonna be a normal mixture where the mean of some normal distribution is distributed itself normally with either mean -1 or 1, depending on the value of z. Then some distribution is constructed with that mean, and y is observed from that distribution. This program says exactly the same thing. There's some z that picks between two distributions, d0 and d1, whose mean is a sample from a normal distribution with different parameter. So you would expect that these two programs would have exactly the same posterior distribution on z, except these two programs are clearly not equivalent, right? How many random variables are in the first program, and how many random variables are in the second program? I see Naomi either flexing her hand or doing something else. So
for the first one, 4.
First one, 4. So we've got 1, 2, 3. I see 3. And the second one?
5.
I see 1, 2, 3, 4.
Off by 1 error.
I mean, you're probably counting from 2. That's fine. It's great. Okay. So everybody see that there's 3 random variables in the first one and 4 random variables in the second one. Don't be confused. These are distribution typed objects. They're not random variables, right? Okay, cool. So they have differing support, actually. So that means these programs actually, in the probabilistic sense, are actually different. But we have a notion of desired equivalence. We would like their posterior distribution on the return value to be the same, right? In other words, if we marginalize out mu in the first program, and we marginalize out mu naught and mu1 in the second program, we'd like both of these programs to have the same posterior distribution over z given y. We could choose a semantics in which this were not true. Okay, that's a possibility, but it would mean that we would have to adjust our understanding of what an expression in the programming language means in order to match the semantics, and that's never a good thing. When we read these programs, we would expect that they have the same distribution over z given y. Okay. Even nastier, what's the third program here correspond to? First, how many random variables are there? Is it the same then? Okay, we're going with 4 random variables. I think you're starting to see it. 1, 2, 3, 4. Good, right? Okay. So 4 are random variables. And is it the same? I would argue it's the same, right? So the mean is either a sample from a normal with -1 or a sample from 1. There's the distribution with that mean. It's observation. So I would say that they're all equivalent to each other, right? And the point is that one of them is an odd duck here, right? So this one has 4 random variables. This one has 4 random variables, right? And if you haven't figured out what eager versus lazy evaluation is yet, this is going to be the fundamental difference between the two interpreters that you're writing, right? So pay attention here. This is probably the only useful thing you get out of this lecture. I'm just kidding. When we talk about eager evaluation, What does that mean? Anybody remember from computer science what eager evaluation means?
No, but I'd say it tries harder than the other one.
It means when you run this if, right? You have two choices. You can either run both or evaluate both the consequent and the alternative, and then pick given the value of the predicate, or you can evaluate the predicate and only evaluate either the consequent or the alternative. So it's called eager when you evaluate both the consequent and the alternative and then pick afterwards, and lazy if you evaluate the predicate and then only do one of the two. And obviously you do less computation if you do lazy evaluation, and that's what running a program would do. But when we assign a meaning to a program, we have to pick a meaning that that we assign to the program, right? So which value, or rather, what meaning should we assign to the program?
I have a question.
Yeah.
So you're saying that there are 4 random variables in the third one because the dark blue words appear 4 times.
Correct.
But 2 of the samples appear within the if statement, which I would interpret that as only one of them would ever be calculated. You can't have both of those being calculated at the same time because only one is activated based on the if statement. So are there...
That's precisely what I was just talking about. So you can either read, so like,
Yeah.
I don't know. You have to tell me what the meaning of the expression is. And when we have random variables, the meaning will change depending on whether we evaluate if eagerly or lazily.
So this would be a lazy evaluation?
I haven't said. We haven't decided. We're not evaluating, first of all. Like, that's the first thing. We're assigning meaning, right? So, but you can either view this as, we can assign meaning either by thinking about this third program as in the eager evaluation way, which is to say that both branches are evaluated, or are we going to try to assign meaning in some sort of a way where we only evaluate one branch? Okay, so let me just skip ahead, right? So this is lazy versus eager evaluation, or meaning, or whatever, and the too long didn't read, argue about it for 6 months and think really hard about it, is that in order to assign a consistent meaning to the program, and by that I mean a meaning that will correspond to your intuitive meaning about what the program could mean if you were to evaluate it in the running it style, what you need to do is you have to do eager evaluation, okay? Which is to say, you evaluate both the consequent and alternate branch. That's what you got to do. There's a bunch of other things that you could think about doing, ways to assign meaning. You could set the probabilities of all the unevaluated branches to 1. This leads to improper priors. You can do a second thing. You can try to augment the values in your compiled to language with nil values for unevaluated branches. It's really complicated. We couldn't get it to work. What works is doing eager evaluation of if expressions. So there's some intuitions about this, like compiling a probabilistic program to a graphical model must account for all of the random variables that the program could generate. Okay, that's the deal, right? So language restrictions, the language restrictions that we talked about for the FOPPL, ensure that this number is finite even when doing eager evaluation. So we're good, right? And a subtle but kind of important point is that stuff in ifs, this should really say like stuff or random variables in ifs down unevaluated branches are blocked from observes on the control flow path and thus can be marginalized out by ignoring them, okay? There's some gotchas here. Whenever we're compiling, we have to generate unique variable names. We have to, and if you think about variables inside user-defined functions, they're called multiple times. We're going to need to be able to distinguish those. And even though we can deal with sample expressions and we can eagerly evaluate them and we can marginalize them out because of control flow considerations and deseparation, observe statements down branches cause problems and have to be treated differently. Okay. So here's the last form of this program, and this program is really annoying. So if we have Z be a sample from Bernoulli, we have mu is either, we have two options for mu 0, mu 1, which is either normally distributed with mean -1 or 1, same observation. And then we branch and say, well, we either observe a normally distributed quantity with mean mu 0, y, or mu 1, y. Okay. Here, things are different, right? It's like, what does an observe, and this is a very interesting problem, right? From a semantics perspective, worth thinking about. What does observe under a branching statement mean? It's not that the random variable isn't there or isn't observed. Like, in other words, it's not like you're missing data where you could observe or not observe. That's one thing you could implement with such a facility, though. It's if you observe different quantities, you can really get yourself in a knot thinking about what it means to have conditional observations. And I'm not going to do that in front of you right now, but if we had time and you want to think about it, we can. So eager evaluations of sample statements, that's optimal. It's what we need to do in order to get corresponding, it's what you need to do. Lazy evaluation of observed statements seems necessary. In other words, this program doesn't really make any sense unless you're doing lazy evaluation of the observed statements, okay? So the solution in order to provide a semantics for first order languages that's consistent with run the program semantics or the expected semantics that you would have if you were to just read the program and interpret it the way you would a normal run it forward program is basically to do eager evaluation, but to also track control flow and to basically to give probability 1 to observe statements not on the control flow path. In other words, if you're not on the control flow path, in other words, if the random variables in your program turn off an observation for whatever reason, we're going to track where you are on the control flow path and actually turn take that observation out. We're not going to count it as part of the probability. And observed statements are given the probability, whatever their corresponding probability is, when they're on the control flow path. Okay. This is a little bit difficult to do in lecture form. It's probably the best I can do. But the point is that the semantics that we're about to go through, we want them to be consistent with lazy evaluators, which is how normal programs are run, and that's how we see programs and how we interpret them as human beings. And in order to achieve this, we need to do control flow tracking in order to remove observed random variables from the trace. But sample statements down traces that are not on the control flow path are totally fine, can safely be marginalized out. So we're going to do eager evaluation to identify all the random variables, but we're going to do control flow tracking in order to count or not count the observed, depending on whether or not they're on the control flow path. Okay, I think today, because yeah, I've done a very bad job of the snack thing and the bathroom thing. I think this is probably the ideal spot for the snack/bathroom break thing. I'm happy to take questions about what we've just been talking about, and then we'll return at 4:15 and see how far we can get. Okay.
Can I ask a question about the if statements?
Yes, please, absolutely. Yeah.
I was reading that section of the book, and it seems how do you say that? Like a really sort of elaborate set of rules that you need to evaluate these if statements. Like, is there some reasoning behind that? Like, why does it end up being kind of complicated? If you understand what I mean, or
if you mean that the rules we're about to go through, then yes. I think like historic. So there's a couple of things, a couple of responses. One, it's not clear that there aren't other semantics that you could assign to the program, right? There are certainly, like, when we were doing this, we were exploring like standard sorts of places, languages that don't have semantics. They just, their semantics are defined by their operational characteristics. Is the way they say it. Like, you run the program and you find out what it means. So first of all, there could be different semantics. Second of all, there could be different ways of treating sample and observe that do the same thing in the end. But when we spent our time trying to figure out how to make the reason for the complication is that we really do want the meaning of these programs to correspond to the meaning that you would have if you were to read it as if you were evaluating the program. Like if you make a Z, make a mu naught, make a mu one on this slide, have a Y, and then eagerly evaluate either of the branches here, right? That program has a particular meaning. That's how we read these programs. And if we were to assign a different semantics, it would lead to all sorts of trouble. In other words, for instance, your interpretation of the graphical model program and the evaluation-based interpreter, which is why we're doing that in homework 2 and 3, those two evaluators would return different conditional probability distributions, because the meaning of this program would be different depending on whether we treat it as a graphical model or compile it to a graphical model, or we evaluate it. And that is the thing that we spent a long time trying to avoid. And it's non-trivial to avoid. There may be other ways to avoid it that are smarter and better, but we didn't come up with them.
thanks.
Yeah.
I'm a little, I don't understand why probability 1 is given to the observed statements, not in the control flow path. Like, what does that mean?
It means that they're removed from the.
Oh, like marginalizing out.
Yeah. So when you have a big, just there's going to be some big graphical model, and this is a terrible notation, whatever. And if you have an observe here and you have an observe here, and I don't know, whatever, and you compute the joint probability of this thing, right? If these are two different control paths, this is, consequent alternative, right? What you want when you write down the joint distribution is you want to have an expression that looks like P of x1, P of x2 given x1, and then P of y1 given x1, x2, or P of y2 given, y1 given x1, x2. Okay, so these would be the predicate and alternative branches, something like that, right? Yeah. Okay. But if we want to pick them off such that the marginalization is correct, we need to actually raise these things to a power. Right? And really what we're going to end up doing is we're going to raise these things, effectively, we're going to raise these things to a power of 0 if they're not on the branch, and 1 if they are. Okay, so when we say we replace the probability, we set the probability of observed to 1, all it means is that we've raised it to the power of 0. So we just remove it from the probability calculation and in that for that setting of all of the random variables in the program. Okay, we're back. I think. Well, we're supposed to be. We kept talking. I kept talking, but there's Naomi, there's Ina, Jason, Baron. Who knows? Okay. So here we go. Hang on to your britches. Time to go. Okay, translation rules. So the translation rules are a recursive algorithm for translating FOPPL programs into graphical models. They're succinct and declarative. Okay, and the notation looks like this. They're logic expressions, actually. If the top holds, then so too does the bottom, right? So there's going to be a bar. So you can do derivations, and you can this is basically how you do proofs about program equivalences. You say, okay, this reduces this, if the top holds and the bottom holds, and I can then say that the bottom on the right holds, so on and so forth. And then you can prove that two programs are equivalent under a particular semantics by reducing them using these rules. That's the kind of thing you can do. Here, they also correspond to the way you would write a compiler. So you can really think about this as an implementation in which there's going to be some expression or some setting of that you're in, which is going to be a particular row, there's going to be a state that you're in, and a particular expression that you want to compile. Then you're going to do a bunch of the stuff on top, and then you're going to return the meaning on the bottom right-hand side. So you can sort of read these this way. That's when you're thinking about implementing a compiler, that's how you read them. The good thing is there's only 8 rules, 3 of which are very, very simple, and the rest you have to squint at for a little bit for writing a compiler. So writing a compiler is actually not that hard if you have a metaprogramming facility and the ability to write these 8 expressions plus partial evaluator. Okay, so the easy ones are the constants and variables. Okay, cool. So no matter what row is, no matter what phi is, when you have an expression which is C, so this is an expression, the meaning of this expression, when you translate it, is an empty graph and the expression C. Okay, so the expression for the return value in the pure deterministic implementing language of both variables constants is the same expression as FOPPL. Neither generates any graphical model component. So if you have a program and the program is C, cool, and you feed in, no matter what you feed in for these, it doesn't really matter, right? The output of the compiler would be an empty graphical model and the expression C. Done. Okay. Same thing for a variable. If your program is, foo, the meaning of foo is a empty graphical model and the variable name foo. That's it. So E equals foo and G equals, empty set, square bracket, whatever. So that's here. Okay. Notably, though, just to make you worry a little bit, you should really also recognize that these are going to be base cases of recursions. Okay, so when we're evaluating expressions, there's going to be some expression like this. Eventually, we're going to get down to some base case where the expression that we're evaluating is this, and the meaning of this sub-expression 7 will be, the constant, what will be, the empty graph G and the constant expression 7. We're going to have a base case of foo, same thing, right? Fine. And then we're going to have some case for function application, and that's going to do something as well. Okay, fine.
Can I ask a bit about the notation?
Yeah.
Because I was looking at the first top two, and I'm wondering sort of what's the difference. So I guess this whole thing with the line and then the things underneath, is that supposed to just, this like the one on the left, it's saying like this is describing the action that is returning C?
This is saying that the meaning, there's two ways of looking at it. There are no logical preconditions. There are no preconditions that mean that we can do this translation that are required in order to do this translation. That's the first meaning, okay? From the like, if this, then this, right? That's one way of reading this. If the top holds, then so too does the bottom. So the top trivially holds because there is no top, so the bottom holds, okay? And the other way of reading it is when you implement it, we have a case like this. There's some row, some phi, some c. Again, we have no rows and phis and c's at the moment, right? We just have a c. So there's nothing you need to do, and all you need to do is make an empty graphical model, empty graph G, and return the same string C, basically, expression, symbol.
So what is this like unit called? Like what? Like why do we have a notation
An inference
for
rule.
it?
It's an inference rule, a translation rule.
Okay.
So let's see. So we've done constants and variable references. Okay, so now we only have 6 translation rules to deal with, and they get progressively nastier. But if you can sort of hold them all in your head, then you'll see the entire thing. Or if you implement it once, or you read the internals of Daphne, or whatever. Okay. Okay. So let expressions. This is case number 3. Note that these are cases in the grammar, right? So as many expression types as you have, right? That's how many of these rules you need to have in order to compile a thing. So that's why we did all the sugaring and all that sort of stuff. We try to make it as small as possible to make the language as powerful as possible, and so on and so forth. So how do we translate a generic expression like this, where E1 and E2 can be other expressions? We don't know what those expressions are. So this is the case that we're in. Okay. Again, this rho and sigma, rho and phi, they're going to show up later. Just chillax on that for a second, right? So it says, again, let's read it in this direction, okay? The first thing that we should do is take that rho and phi, whatever those happen to be, and E1. So we're going to pull out this expression, E1, right? We're going to put it up here, and we're going to go match that rule to whatever the rule is for E1. And that E1 could be some other complicated sub-expression, who knows what, right? And we're going to translate that, and we're going to get some graph G and some return expression E1 for that sub-expression, okay? Notably, this graph is going to be all the graphical model nodes and edges and all that sort of stuff that would be generated by the expression E1, and whatever the value of E1 is, as is related to the random variables that are generated. Yes, I could definitely say big E1. Yes, sure. And then big E1 is the value that small E1 would take given the random variables in big G1. Okay, next thing we're going to do is we're going to take E2 and we're going to do the same thing, except we're going to do something interesting, right? And this is notationally interesting to think about. So in E2, and this payment relates to, if you're still here, payment still here, still paying, not even really paying attention, but maybe I'll get him to pay attention now. When we're talking about pass by value, right, and where it doesn't really matter whether or not we have pure data structures, what happens is that V is substituted. This is not bound to, this is substituted. So literally, we take the expression E1, big E1, excuse me, and stick it into the expression little e2.
Is it an input to little e2, or does little e2 then take on the value?
It's really rewrite E2. So if E2 is plus, plus F10, and somehow we've translated so this is going to be that's a bad example. Let's do something like plus F217. Something like that. Oh, we're in let. Let me do let. Let A be plus 7.2 plus AA, something like that. Now, E1 would be this thing. Little e1 would be this expression right here. In the case of pure function application, it's a little bit complicated what's going to happen, but this you can think of as being translated to E1, and I'll tell you that E1 here is, before partial evaluation, going to be exactly the same expression because there are no sampler observes. Okay. That means that when we do the substitution into little e2, what that means is that this expression, e2, gets translated to plus 7.2 plus 7.2. I.e. truly call by value, but we're really not calling by value, right? We're literally substituting the entire expression in. Okay. And then this expression is translated recursively. This is where it gets kind of mind warpy to think about this, and these people who can think in these notations are pretty impressive. I had to learn it in order to even follow along with this. That gets translated to some graph G2 and some expression big E2, which corresponds to the return value, or basically the meaning or value of E2 with V substituted for big E1. Once we've done that, we have a big G1, a big G2, a big E1, big E2, and the meaning of this let expression is the combination of two disjoint Bayesian networks. And the definition of this notation, circle plus, is to combine the vertices by taking the union, the edges by taking the union, the set of link functions by effectively concatenating two finite maps with disjoint domains. We're just going to take the link functions, smack them into a hash map, and then same thing with the observed values y. Yeah?
Is there any relation between G1 and G2? Because G2 is defined based on E2, which is defined based on big E1.
So G2, big G2, will generally only have new random variables if the expression little e2 has sample or observe expressions in it. So in this particular case, you would expect big G1 and big G2 to be disjoint, except that, so they would be disjoint in their vertices, but they are almost certainly, well, they may not be disjoint in their arcs or edges, because little e2 could refer to sampled random variables that are shared in common with E1. So that the arcs should be disjoint, but they may refer to the same parents.
The arcs being edges?
Edges in the graphical model, yeah.
So
This is these thinking this way for the very first time for somebody who has not written a compiler or isn't a computer scientist by training, and I don't know if you are or not, but I think not. Thinking this way the first time is very hard. You kind of have to do it and actually do a couple of examples to really get what's going on. I'm doing the best that I can. Hopefully it's making a little bit of sense. We'll go through some examples of what happens. In particular, this is an example here. So I basically read all this. So E2 with V is a result of substituting the expression big E1 for V and the expression little E1 while renaming bound variables of E2 if needed, little E2. And then the combination of two Bayesian networks is defined this way. It's pretty straightforward. You smack together the vertices, you smack together the edges and the link expressions and the observed. Yeah, great. So an example of this is, here's a very simple let expression, right? There's no sample statements, there's no nothing. This will translate to this, and I can't do too many levels of recursion, otherwise it gets really crazy. So we're gonna do the smallest set of recursions we possibly can. So we know, for instance, that little e1 here is 7, and we know that 7 translates to the emptied graph and the expression 7 because it's a constant. And then we evaluate the body of Z, this expression Z, where we string substitute the string Z everywhere Z appears. Okay. So that returns G empty and 7. So G empty union G empty or combined with G empty is just G empty, and this whole thing evaluates to 7. Done. Basically, it's taken the value of 7 and shoved it into the expression and then translated it. Okay, here's where it starts to get fun.
Wait, before we move on, it almost looks like the right-hand side on the let, sort of that kind of takes care of the evaluating of, sorry, not sure evaluating is the right word here, but of the variable case before. But because you're already kind of substituting that variable with 7, so you're not.
Are you talking about this?
Yeah, exactly.
Yes. So you are 100% right. If you caught this, this is really, there's a teeny tiny little hand wave here, which is the bottom of this recursion requires one more step. That's why it gets a little bit complicated. Sometimes when you see these things actually written out, you will see that there's a line above this and a line above that and a line above this. The base case of this recursion is actually to identify that Z itself is a variable name.
Gotcha. Yeah. Okay. Yeah.
Right.
Yeah.
Yeah, exactly.
Sorry, can I just ask? So, and like this let statement, so if like the program was longer and there were like other statements who are dependent on Z, will this translate, like, will all the Zs translate to 7, or they're gonna stay as 7?
If you're saying that here this were a more complicated expression, like plus Z times Z whatever, yes, then the translation would be times plus 7, 7, 7. And so on and so forth.
Thank you.
Yeah, of course. Good question.
I have a question.
Yep.
I'm still having trouble understanding this sentence that says here E2 V is equal to big E1 is the result of substituting E1 for V in the expression E1. So I'm a bit confused by that because I don't see like a little e1 where we say e2 of square bracket v. So what is little e1 here when we say that it's the result of substituting?
Wow, what a terrible
Okay.
That's really bad.
A bit more
Thank you.
sense now.
Okay, thank you. I've never ever, yeah. The part of the issue is, yeah, I just read the translation rules, and when I look at those other, I just, yeah, that's my typing error. My bad. Sorry.
It's okay.
Remind me afterwards. That's a nasty one. Yeah. Okay, if expressions. Let's see if we can get through this. It's gonna be fun. So we talked about eager evaluation, so I think we can go just a little bit faster. So modulo something, we're starting to get it. Like if expressions eagerly translate the predicate, consequent, and alternative branches, building a control flow predicate at the same time. And the reason why we're going to do this is we're going to dynamically include or exclude observed statements. And then we rewrite the if expression in the pure deterministic language. You'll see exactly what happens here. Okay. So here we are. We're in this case. So we're in some. We have some package of functions. This row is going to be really trivial when you see what it is. Now is the first time we deal with the phi. And this phi is yeah, it's fun. So the phi isn't going to show up, and it's not even going to show up over here. You'll see what ends up happening. So what happens? So here's our expression, if E1, E2, E3. So we're going to do eager evaluation, which means that we're going to translate E1 to G1, big E1. Okay. Then we are going to change the row that we use while we're doing the translation. And we're going to say, and phi, big E1, whatever big E1 is. So that's if you remember, that's going to be the value of the predicate, right, in the pure deterministic language. All right. So that this expression, particularly if phi starts out as true, will evaluate to true if big E1 evaluates to true. Just keep that in mind. Then in this context, we're going to evaluate little e2, and that's going to result in some graph big G2 and some return expression big E1. And we're going to do this one last time with row, but we're going to do something funny here. We're going to say and phi, which again you can think in the base case is true, not value of big E1, which is to say this expression will evaluate to true only if we're going down the alternative branch, or rather the random variables in the program take values that would mean that we should use observed expressions in the alternative branch. Little e3, we translate little e3 in this context to a graph G3 and a value expression, return expression E3. Which means that overall, in this context, what ends up happening is that we merge the graphs G1 to the G3. That's our resulting graph. And we are left with a pure deterministic expression if whose value takes either big E1, big E2 or big E3 conditioned on the value of big E1. So a somewhat uninformative example, but something that we can put on a slide is, if we've just done the translation of this, right, this inner expression, so we know how that gets evaluated or transformed. So if we have if true that, then this, we evaluate the predicate, that returns the symbol true and an empty graph. Then we evaluate in this context, which has been updated with phi and true. That returns the translation of the let expression, which we already know as the empty graph, and 7. The last one is row, and then this funny expression and phi not true. We get the constant value 8 back and an empty graph. We merge all the graphs. There are no random variables. And the return expression is if true 7, 8. Okay. Cool. Totally makes sense. Now, a little bit of foreshadowing. partial evaluation has a role to play. This is a very silly to carry around this kind of expression because we can simplify that, and it will turn out that we need to. And it's a little bit boring so far because we have no function application or random variables, right? So I guess we have 5, 6, 7, and 8, I guess is what we need to do now. So 5 and 6 are very similar. So 5 and 6 are user-defined procedures and primitive procedure calls. So this is the user-defined primitive procedure call. And hopefully at this point we can start reading these with a slightly more pace. So we have the context and so here's the case that we're in. There's a user-defined primitive procedure f and some expressions e1 to en, and we're going to evaluate those or transform those into some graphical model and return expression. And the way we're going to do that is all of the inner expressions e1 to en, we are going to recursively translate to big EI for all of the arguments. Then we're going to look up, or again, this is satisfaction on the top, but what we're going to do implementation-wise is to look up in row the definition of the function f, this function here, and then we are going to substitute in the expression, just like we did before for let, big EI to big E en for all the variables v1 to vn in expression e, little e, which is the body of the function. And then we're going to translate the body of the function to return a graph G and a return expression E. Okay. So again, this says we're going to generate values, which are just expressions for all of the arguments, and then we're going to actually just replace those. We're going to stick those into the body of the function, renaming all of the variables in the function as we go appropriately. That make sense? Okay, cool. Primitive procedure calls are even easier. Here we just translate all of the argument expressions to graphs, and then we return, or our return expression is just the primitive procedure evaluated on the return expressions from having translated all of the argument expressions.
Could you repeat what you just said? I heard we translated all to grass, and I don't think that's
clearly grass has nothing to do with it. That's what we do on spring break. No, so we translate all of the argument expressions first. That's what this says. We're going to translate all of the argument expressions. Then, and those return big EI for each of those expressions, graph and return expressions effectively for all of the little EIs. And we merge those graphs and we call the original primitive procedure with expressions from the translations substituted. Sorry, that was I have no idea what's happening, but I'm going to smile and let him go on anyway. Okay, cool.
I realized you said graphs.
Yeah.
Yeah,
graphs. Yeah. Okay, so this is what I've just gone through. Great. So if we have a function like this, my polynomial x, so on and so forth, and we have a function application, my polynomial with an argument 8, under these translation rules, that would translate to an empty graph, and the expression given here, or the value, or this expression 8, don't think of it as a value, it's the expression 8, is text substituted in for all the variables x. Okay? Fine. Cool. Sample expressions. We finally are there. 7 and 8. the last cases, almost. So
sorry, so for the previous one, can you have function overloading here? Or we can only define functions with unique names?
So remember that there's only one way to define functions in this language, which is def in at the beginning.
Mm-hmm.
Right? And that is a global map. So the meaning that yeah, so basically you need to define unique function names. Yeah.
So like you couldn't just like define this like row mapping as like function name plus number of arguments or something like that. You can,
but then you have to then you change the operational semantics, and that would not be a hard change to make, right?
Oh, okay.
Right, basically, it would say that this map is not indexed by just f, but it's indexed by f and, for instance, number of arguments. Right.
Okay, makes sense.
Okay. All right. So what are sample and observe doing? Okay. Here we go. So we're in an expression like this: sample e, whatever that is. Okay. What are we going to do? Well, the first thing we're going to do is we're going to translate the expression e into a graph. And just to be clear, this graph breaks down into a set of vertices, a set of arcs or edges, a set of link expressions, and a set of observed variable bindings y, and some expression big E. We're going to choose a fresh variable, which is to say we're going to construct some random string, which is guaranteed to be unique in a particular compilation pass. So that would be v, for instance. We're going to look at the free variables in the expression e, and I'll explain what free variables are in a little bit, but basically they're any variables whose value is unbound. Another way you can think of it is they're going to be the parents in the link expression, right? The link function expression. So there's going to be some free variables. We'll call those z. And for this expression, big E, we're going to construct an expression by calling a function score. Not terribly important, but basically what it does is it takes the expression E and translates the distribution type into a PDF evaluation function. That's fine, doesn't really matter. So long as we're able to do that, we can construct an expression f. This will be clear in just a little bit. Then we do the following. We augment the map of v of variables with a new random variable whose name is given by the expression v, the fresh variable name v. We link v to all the parents and the parents are the free variables in the expression e, again big E, where again that's the translation of this. So there's going to be some sample normal plus x y z times z, something like that. So this expression is going to have free variables x, y, and z. Shouldn't have used x, y, and z. I, j, k. It's going to have free variables I, j, k. And that means that our new variable v will have parents I, j, and k because they are the free variables in this expression. Cool. Fine. Then p will be augmented with a new map entry which links v, this new random variable, to its density function expression, which is again going to be basically this exact same thing, except you're going to take this normal and return, you're going to write normal PDF and the variable name v here, and then the link expression to get the arguments. Y is unaffected because there are no observed variables, and the value, the translated value of the sample expression, and this is where it gets interesting, is the variable name. This is the only time that we've actually generated a variable name. Okay.
I have a question.
Uh-huh.
So, what does f not equal to perp mean?
So this is referred to as bottom.
And what does that mean?
And it means that provided that it's possible, so bottom means fail. Okay. So like in programming languages, you have to have a value for the program doesn't work. It stops, right? So that value is outside of the return type of the program, right? So a program, the set of values that a program can take is always the set of its return type augmented or unioned with bottom, basically. And again, you can look in the book. I don't think I even have slides for score. I don't remember for sure, but score again just translates translates an expression that looks like a density, looks like a distribution constructor to a density evaluator. So basically, this fails if the expression capital E is not a distribution constructor, and if the distribution constructor is of a type that is not implemented in the underlying language or not recognized in the underlying language. Okay. Good. Okay. So
Can I also ask? Yeah.
Yeah.
So in the procedure, when we're mapping V to F, no, it's like the next slide. Yeah.
Yeah.
So in the evaluation, so we have like this big P, and which is the procedures, right?
P?
P?
No, those are the big P are the link function expressions.
Oh, okay. Yeah. Sorry. So we're mapping V to this F, like the big F.
Uh-huh.
Do we do that everywhere in P?
So that notationally, sorry, again, this is, we got to look in the book and we got to notationally, that arrow means map to, it doesn't mean substitute, right? So notationally in the book, you will see that I'm trying to find the substitute thing again. This is substitute. And this is hash map. Make an entry in a hash map with key V and value expression F. Okay.
But can we have like other expressions that are dependent on this V? Because like I played
Indeed. So this is okay. I think I know where you're at now. So this sample, the meaning of this sample is the variable name V. And this variable name will be used in other return expressions. Right, so basically we're defining a unique variable name that corresponds to this sample statement. Okay, so I guess this is a this is a worked example, right? So provided that you're okay with normal 7.1 translating to empty graph normal 7.1, which it does because they're just primitive procedure applications and whatever. Then this sample expression, this larger expression in this let, says, okay, translate the inner expression to some graph and some expression, create a new random variable name, that's this fresh variable, look for the free variables in this expression, of which there are none, because there are no variable names in there, so that's empty. Then we translate the expression big E, which again is here, into a density evaluation expression, paying attention to where, basically with the variable name v in it, that's v here, right? And then we construct a new graph or augment our graph with a variable name, all of the edges of which there are none, a map which goes from the variable name to its density expression, a binding of random variable values, of which there are none, and now we have a named variable that can be used recursively in subsequent expressions.
Can I ask a question?
Yeah.
So this variable name, and I don't know if this is the right way to use it, but can you use, like, if you were to like print it, so to speak, it would return like normal PDF X, whatever variable name is, like it would return the normal distribution defined there, like that's what that variable name is tied to?
Everything we're doing is manipulation of expressions. So there's nothing that's being evaluated except to say that the evaluation, hey?
If so we're returning this variable name.
Yes, this one right here.
Yeah. And I guess I don't fully understand what it represents. Like,
great. I think the next part of this example. So now I'm going to translate the let, okay, and the second sample translation. So again, you have to do to do one of these out all the way. You either have to implement it or you have to actually do it out by yourself one time to like see how it works. But this last thing, if you remember, we have the rule for let. What does let say? It says take the translation of whatever the thing over here is, take this translation and literally plug in the translation into the body of the let expression, right? That's what the let thing did. So the translation of sample normal 7.1 is this variable name. That is the expression. So now we can actually take this variable name and translate, the body sample normal, x17171, and that is the expression that we're going to now translate. And when we do that, in this second, when we do the let expression substitution and then translate this expression sample normal x1, what we're left with when we use the let rule substitution and we do this sample translation one more time, what we're left with is now two random variables, an edge that gets created because there's a free variable in the link expression, a density evaluator for the first random variable, a density evaluation for the second random variable, which has the first random variable name in it. And again, there's still no observations. And the return value from this would then be, or the value of this expression would be the variable name generated by translating this second sample expression, the body of the let. Okay. So your question about where does this variable name go after we do the translation, well, it is the result of translating this expression. And it gets used recursively in all of the other rules because all the other rules require a translation of the bodies or their arguments or so on and so forth before they themselves get translated.
So,
So
in that second sample statement, the function free vars will evaluate to the variable that you generated in the first sample statement. Is that right?
Correct.
So, oh, Bernd, was that all? I don't want to interrupt her. Okay. So the first variable name we came up with, it represents the normal distribution.
It represents the random variable. It represents this random variable. No, in particular, it represents this random variable.
Okay, so it represents a random variable pulled from the normal distribution.
It represents, yes, in this particular case,
No, yeah,
generated from this. Yeah.
But because that's defined as a normal distribution, it represents a random variable pulled from there.
Mm-hmm.
Okay. Thank you.
And not only that, the critical part is, particularly when you focus on this second sample expression, now we're getting very, very, very concrete about what this program means. Very concrete. It means that there are two random variables. There is an edge between them, and the densities for those two random variables are given by these expressions. That's what this program means. That's the translation.
I have another question.
Awesome.
So, like this variable x1717.1, like why isn't it substituted as like normal PDF x1717.7.1, like in the variable x23232? Because like I told it, when we have let, we literally just like copy paste the whole expression.
Ah, great. Okay, let's go back to let just to make sure that we see what's going on. Where's let? Let is here. We substitute the result of translating the inner expression, right? So we translate E1 to something, and I'm saying very, very, very concretely that the translation of a sample statement returns this expression. It returns that expression, the variable name. So when we substitute, we're substituting big E1 as Emma asked me to say. We're not substituting little E1, right? So we're substituting the variable name that we've just translated to. Does that make sense? Sort of enough?
Yeah. So it's all about notation.
There's a lot of notation, and like this is what y'all were like, your notation sucks. It's not clear. Well, this is clear. It's just really, really, really notation heavy, right? So it's complicated, right? Like dealing with the mathematical objects, which are programs, requires a very, very serious kind of notation, right? Oh, we do have score in here, but I already said what score does, right? Sorry. So score does a bunch of stuff, but it basically says if there is a constructor for a distribution, then it just translates it into the density function evaluated at that value. Okay, let's do observed expressions, and then maybe we'll see the whole thing come together. Okay, last one, last rule, 8. You've seen your first compiler if you haven't seen a compiler before. What does observed do? So we're in this context. Here we're going to care about this phi for the first time. It's going to be a little bit crazy what happens, but hopefully everybody can hang in there and see what happens. So we know that E1 needs to evaluate to a distribution object, and E2 has to evaluate to a value, or the meaning of E1 has to be a distribution object, and E2 has to be a value. Okay, so there's a lot of stuff we do when we get to an observe. The first thing we do is we translate E1 using all the rules that we had before, and that's going to generate some graph and some new expression. We're also going to translate E2, and that's going to generate another graph in some expression. Then we're going to merge the graphs because we can in this particular case. That's totally fine. We're going to choose a fresh variable. In other words, we're going to name this random variable as well, right? That's fine. We're going to look at E1 and do the same score thing. We're going to construct a probability mass function for the observed random variable. Cool. And that's going to have the random variable name that we've just defined in it. Now we're going to augment f, and this is the crazy part. We're going to augment f. We're going to make the f that we actually add to the link function expression thing here. We're going to say if phi, then f1 otherwise 1. And what does that mean? What this means, the log probability of, or rather the probability of the observed variable v is going to be either f1, which is its density under the expression E1, which is basically the density under the distribution specified, or 1, condition on the value of the expression phi. But if you remember, the value of the expression phi tracks the control flow through if expressions. So if we go back to if expressions, phi becomes dependent on the value of the guard or predicate. Okay. Fine. So now we have the density expression. We look up the free variables of the density expression. We make sure that there are no free variables. In other words, there are no random variables in the expression for the value, because that would change the semantics of observe. So E2 has to actually be a pure deterministic computation. B is now just a set of edges from the free variables in the link expression to the new random variable name. And now we can construct our new graph and the value of observe. And the value of observe is just the value of whatever this expression E2 is. Okay. I really kind of wish that I'd kept this homework in just so you would actually write the compiler, but this is what Daphne does for you, okay? So in summary, we have these 8 recursive rules for compiling FOPPL programs to graphical models with pure deterministic link function expressions: constants, variables, samples, observes, let, if, and function applications of both kinds. I'm going to okay, maybe I'll do this again next time, but we'll say this program, which just samples 2 normal expressions, this is a joint expression, just generates 2 random variables, 1 edge, and 2 normal PDFs, no observed variables, and the return expression is whatever the name of the last random variable is, okay? Which means that you can construct this as a graphical model. You know all the link functions. You can evaluate the density by looking at these. You can see all the random variables by looking at these. And you can run the program by sampling in this graphical model and evaluating the return expression. This one, sample beta, Bernoulli, observe under Bernoulli. This is a posterior distribution of plus PP, whatever the heck that is. This, under the compiler, will translate to 3 random variables, 3 edges, 3 density expressions, a binding of the observed variable name, and a pure deterministic return expression that gives you the value of the program, or the return value of the program, conditioned only on given and with free variables that are names in the graphical model. Okay, and same thing if you keep going. So the linear regression example will translate to a bunch of vertices, a bunch of edges between all of those, all the conditional density expressions, which will include all the maths that need to happen. So like we've been looking at linear regression examples, or you will start running those in your code relatively soon. So at the end of the day, this whole thing is going to translate down to a graphical model that you can actually manipulate using arbitrary graphical model, inference, learning, sampling, optimization, whatever tools. And unfortunately, I should probably stop there because of time, but I will need to talk about partial evaluation next time, because if you don't have that, you will be a little bit confused about what's going on. So I'll leave it on this slide, and we can, if you want to, think about what this means. Or you can ask questions.
Can I ask a question?
Please, absolutely.
Is so like to me, it seems that really the only reason we're keeping track of phi is to make sure that we're not observing down branch of an if statement. Is that right?
That's correct. Yeah.
Clear?
And that's really to keep that really keeps the semantics between lazy and eager evaluation the same. And you will find, if you get into, like, it's very strange. Like, for instance, Stan has a very strange semantics that will really, really mess you up when you write down a model if you don't think about what you're doing, because they have conditionals, but they actually count all of the densities no matter what, right? So your conditional observations are all eagerly evaluated, and it makes it a horrible mess, actually. You can really get yourself in trouble by thinking you're doing one thing and actually end up doing a different thing when you're conditioning.
Yeah, so this is the opposite of what we're doing here, right? Like, so here with observe, we're not evaluating the no branch.
That's correct. So the random variable exists, but its presence in its impact on the joint probability is controlled by and this is the part that's maybe a little bit difficult to visualize unless you've actually written the compiler and you really actually see what's going on. Its presence in the joint probability is dictated, and I'll say it again and hopefully this lands, it's dictated by an expression that returns 1 or the probability, but the expression contains the guard expressions for all of the if expressions. And those guard expressions can be and are expressions of all the other variables in the program. So what observes get turned on and off, and this actually gets really interesting, is a function of the random variables, potentially all of the other random variables in the program. So, if you want to look at like a research project, or those of you who get into, like optimization in like mixed continuous, discontinuous, or optimization in models with discontinuities or whatever, this language and translation gives you immediate access to exactly the discontinuities, because they're described by these guard expressions, right? And we did some nasty heavy lifting work on Hamiltonian Monte Carlo for probabilistic programming that basically says that you can demonstrate that like the set of discontinuous program values is measure 0 in the set of values that the program can take, and then Hamiltonian Monte Carlo is actually okay, but it's inefficient, and you can do fancier, smarter things because you want to look at sort of the subspaces of random variable space in which you are on a continuous subset, and like identifying those is an interesting problem. And from an optimization perspective, if you're doing optimization in the space of the latent variables of the program, in other words, you're doing map inference or something like that, that if you have control flow structure, you have this discontinuous structure, and like what to do about that is, who knows, right?
What is a guard expression?
A guard is the same thing as the predicate, and predicate consequent alternative. Like a guard says, are you going to go, or which way are you going to go? It's a sort of a generalized, More questions, comments, worries, considerations? Are you happy that Daphne was provided for you this year instead of having to write the compiler? Can you, given, so obviously the homework has two things in it, right? One is the we're just sampling from the joint distribution, but you can presumably see the JSON output of Daphne and relate it to what we've just been talking about right now. That's really the point of going through this, right? So you're going to get output from Daphne that looks like this when you ask for a graphical model, and you're going to get output from Daphne that looks like a desugared FOPPL program when you ask for a desugared FOPPL program. And you evaluate those two things, one by doing a walk on the graph, and the other one by actually evaluating the program using the rules that I talked about the other day. And you should be able to sort of test yourself by making sure that the two line up, and your understanding of what it means for the semantics of the program to be of FOPPL to be designed the way they are will become established when you see that the two of those actually result in, for instance, the same joint distribution or the same distribution over the return values of the program. Right? And ideally, you would also, hopefully at this point, if you can believe that such a compiler can be written, and you can get a representation out like this, where you have all the random variables identified, all their link functions identified, all the observed variables their variable bindings specified, all the edges specified. Given what we've learned about sampling, you should be able to write a sampler in this representation in a general purpose way, right? And that's the beginning of Prog, which is to say, you have a program, doesn't matter what program, and I'm going to be able to marry it to an inference algorithm, and those two can be totally separated. And the interface between them is some formal specification of a problem, and the formal specification of a problem can be transformed, in this particular case, into a meaning or representation that you can run graph-based algorithms on, which is cool. And you can solve all kinds of crazy stuff this way. If you look at one of the, I don't know if Baron has and Christian have finished doing it, but we were just for the fun of it looking at adding an extra homework just for the fun of it, or making one of the programs a finite horizon MDP planning problem, right? Which we can just, you just do it. So that kind of problem is expressible in a FOPPL, no problem at all. Yeah, Namrata, I see you were about to ask something. Yeah, there you go. Yeah.
Yeah. So I was looking at the outputs of Daphne for both desugaring as well as graph-based sampling of the test that you've provided, and I noticed in the graph-based setting, in some cases the output is already been evaluated. So for some tests, so if it's a +5.2, the output expression from Daphne is already a 7.
So this is what I couldn't quite get my pace up to today, so I apologize for that. If you'll notice, the next slide is the topic of the next slide is partial evaluation. And I'd be happy to stay and talk about it, but it's unfair to all of you. It's already unfair that I stay so late and talk anyway. But I know you love it as much as I do. The partial evaluation, basically in the graphical modeling context, we also have to do partial evaluation in order to get the link structure correct. Thanks, Naaman. So yes, the graph structure will actually have some of its expressions already partially evaluated. That's the end. That's unless I unfairly actually lecture over the next 5 slides. Yes, that's a good thing to notice. Yes, that happens. It has to happen for a technical reason. More questions, comments?
I have a comment and sort of a question. So I was also playing around a bit with Daphne, and I noticed that like for the probabilistic test number 4, if you use like the graph of options, so you get like this JSON file with like all the graphs and stuff. There were like some expressions which were evaluated to none. So
I can answer that. This is a thing that wasn't quite finished yet, and I was just hoping that no one would be so keen. This is actually like a small issue in Daphne, and it should be fixed now. I haven't tested it myself yet. Like Christian said he fixed it, so like re-download Daphne and it should be good. It was something having to do with hash map. Basically, hash map wasn't working quite right yet, but it should be fixed now.
okay, thank you.
Extra credit, extra points to Ina for being an eager evaluator. Pun fully intended. Okay, anything else?
I have a question.
Awesome.
Where do we prevent recursion?
So that went by quickly last time when I was defining the language. So there are no first class functions.
Okay.
All looping constructs are sugar whose bounds have to be defined at compile time. And the one thing that cannot be syntactically specified, but was specified in one line in the slide, is that the def-in blocks at the very beginning, like the function definitions at the beginning, cannot refer to functions that are defined below, nor can they refer to themselves. And if you can't refer to yourself in a function definition, then you're basically out of luck. There's no recursion.
Okay. So for that last part, does the compiler throw an error if we try and self-reference a function?
Yeah, you can test and see what happens. I would guess that the desugar wouldn't care, and I would guess that the compiler will barf in a terrible way, in a way that might chew up all the RAM on your machine and crash. Yeah.
Okay. Thank you.
That would be my guess, but you're welcome to try. Anything else? Thank you for your time and attention. As always, it's been a pleasure, and I look forward to seeing you on Thursday. Have a good evening.